Hello everyone, welcome to our new video. We continue with our first order differential equations. So let's look at a few more examples first. In the first example, we are given an equation here, dy over dx equals to 2x squared y squared. And the initial condition, y of 1 equals to minus 1. So here we need to check in order to say something about the uniqueness of the solution here. We have this f function on the right hand side. Here you have this y prime, and on the right hand side we call this as function f xy. So we need to check that f and the derivative of f with respect to y, which is equal to 4x squared y. Both functions, we notice that both of these two functions are continuous for all x, y values. So according to our rule or theorem, at this point here, x equals to 1, and here this is covered within the continuity region. Therefore, we have unique solution around this x equals to 1 initial condition. Okay, and another example, y dy dx equals to x times ln y. And initial condition is given for, again, x equals to 1, right, y equals to 1. And one more time, this is our function f, so x times ln y, and take the derivative with respect to y, you get x divided by y. So if we pay attention here, we have for x equals to 1, we don't have any problem with the continuity of both functions. So as long as both of these functions are continuous, we say we have a unique solution for this initial condition, x equals to 1. Another example, again, derivative of y with respect to x equals to, on the right hand side, the cubic root of y. This is the initial condition at x equals to 0. So if we look at this now, y over 1 over 3, and the derivative of y is given as y to the power minus 2 over 3. So it is in this form. So as we see, this is at x equals to 0, we have the continuity for both functions. So at 0 and 1, around this point, we have a unique solution. However, if we had the initial condition like this one, okay, suppose we had this initial condition, then we will not have continuity at y equals to 0 because of this problem here. We will have 1 over 0. So that will basically violate the continuity that we require. Okay, so in that case, uniqueness is not guaranteed. But for the initial problem here, we are okay and we have continuity. Therefore, we have unique solution. Another example, this time we are given y prime equals to f, which is equal to x minus 1 over y. And initial condition is given at x equals to 0, y equals to 1. So first of all, at x equals to 0, y equals to 1, function f is okay. I mean, we don't have any problem here. And what about this one? Again, the derivative, we have x minus 1 divided by y squared. So the problem is again at y equals to 0. As long as y is not equal to 0, we have continuity. Therefore, at this initial condition, uniqueness exists, right? We have a unique solution guaranteed. Another example, y prime is given, another case, let's say x equals to 1, y equals to 0. So the only difference now, we changed the initial condition slightly different. So x equals to 1, y equals to 0. But this point, we have the discontinuity for both f and for f of y. So for both of these, we have discontinuity. Therefore, unique solution is not guaranteed in this case. Okay, one more example. F equals to ln 1 plus y squared. Again, this is actually y prime equals to f, actually. So the initial condition is given here. X equals to 0, y equals to 0. So this is our f. And the derivative of f with respect to y, this is what we get. So the denominator is always okay. Here for y squared, again, this is also okay. So this is continuous everywhere, including this initial condition. Therefore, unique solution is guaranteed. No problem. So now we will talk about the differential equations, first order differential equations, where we can separate the x and y terms from each other. So as long as we can write down this right-hand side of the first order differential equation, this h, if we can separate into two functions with g that collects all the x terms and times h, which collects all the y terms. If we can separate it in this way, then solving these type of differential equations will be more straightforward for us, because we can actually rewrite the same product form as a division, and actually y prime we will be able to write in terms of dy over dx equals to g over f. Therefore, this will be f times dy equals to g times dx. And we can basically integrate both sides of the equation and obtain the solution by the result of this integration. Of course, we have an integration constant c, which is arbitrary. Now let's look into some examples. Dy over dx equals to minus 6 times xy. Initial condition is again given, y of 0 equals to 7. So this is an example of separable equation, because we can collect all the y terms on the left side and all the x terms on the right hand side of the equation. And since we are able to do this, we can integrate both sides of the equation and then write down ln y equals to minus 3x squared plus c, and we can obtain the solution for y. And notice that this constant c is arbitrary, so actually we can consider this as c star, for example, and then we can let a c value equals to e to the power, for example, c star. So we can always make this kind of one-to-one transformation here and substitute this c star with another arbitrary constant by letting c equals to this e to the power c star. So we can abuse the notation a little bit. Sometimes I don't write a c star here, but just keep it as c. This is an abuse of notation without loss of generality. We can just actually rewrite this as another arbitrary constant c times e to the power minus 3x squared. Of course, then we need to solve for c by using the initial condition, and we can use this y of 0 equals to 7, and this means c equals to 7. So now we obtained here the special solution. Another term that we have to keep in mind is the so-called singular solution. Basically, a singular solution is the solution that we cannot obtain by giving values for this arbitrary constant c. So for example, with an example this will be more clear. Suppose you are given y prime squared equals to 4 times y, which is not a linear equation. It's not linear differential equation, but it is first order differential equation. And we can check if this y satisfies our problem. And indeed, yes, this is the solution for this problem, but we can plot our solution, the family of solutions actually with respect to different c values. For example, if c equals to 0, we are going to get this curve here. If c equals to 1 here, then we will get this other curve. If c equals to 2, we will get the other curve here. Or if c equals to -1, that's going to be, here. So as we see, depending on the value of c, we have infinitely many solutions on this basically horizontal lines. Basically, the horizontal line that intersects all the solutions is given by the y equals to 0 line here. So this is the y equals to 0 line that is passing from the x-axis. So this is tangent to all the solutions for the arbitrary c values. So that means y equals to 0 in the previous slide. That's the singular solution because it passes through all the set of solutions, but we cannot actually obtain y equals to 0 solution by giving the values for c. Another example, suppose y prime square plus y square equals to 1. So we have, let's say the solution we have obtained is y equals to sine x plus c. Again, for different c values, we can draw these functions. For example, if c equals to 0, we have the sine function. This is the sine function here. As you see, that passes through the point 0. At pi over 2, it is equal to 1. And it basically oscillates around this x-axis. And for other c value, we will obtain these shifted versions of the sine curve. So all these solutions, they have two tangent lines. One of them is this line here, y equals to 1. Another tangency line is y equals to -1. So both of these are singular solutions that cannot be obtained by giving values to the c. As we summarize here, y equals to plus or minus 1 gives us the singular solution, and basically we can obtain these from the tangent lines. This is also called as the envelope curve that basically describes the singular solution. Okay, now for the existence uniqueness, basically we have the p of x and q of x functions if they contain this initial value x0, and if we have the continuity of p and q on the interval I, which includes this x0, then basically we will have the existence of the solution. And we can apply the so-called integration factor method for these type of problems. So here we describe what do we mean by the integration factor. So actually our differential equation is going to have this form given in equation 1. So if we encounter this type of ODE, which is first order again, then we can directly apply the integration factor method. And how do we apply this method? Basically, we multiply both sides of the equation with this function mu, which we call as the integration factor. And then we think this as derivative. So basically, we consider this left side as the product rule of mu times y. Okay, if we can show that the left-hand side of this equation is actually the derivative of mu times y, that will require this condition to be satisfied. So if this is satisfied, actually the left side of here of this equation becomes the derivative of mu times y. Okay, as a result of the product rule. And therefore, we can actually write this mu prime divided by mu equals to p of x. And then you can notice that this expression is actually the derivative of ln of mu x equals to p of x. Ln mu of x equals to integral of px dx from here, because we integrate now both sides like this. And then in the next step, basically, we can write mu of x as e to the power integral of px dx. So this gives us the integration factor. And then in the next step, basically, once we find this factor, we multiplied both sides of the equation. And on the left-hand side, we obtained the derivative of mu times y. And on the right-hand side, we have mu times q. As you notice, mu times q is on the right-hand side here. And on the left side, basically, we show that this is the derivative of the product mu times y. Then integrate both sides here. Integrate both sides. We end up with an arbitrary integration constant, mu times y equals to this expression. And then, of course, you will write it for y. That's going to be the general solution here. Y of x equals to integral of mu x q dx plus c divided by mu x, or mu x equals to e to the power px dx integrated. So basically, at this point, we have already actually obtained the general solution. If you want to be more specific, you can write y of x by, this is e to the power minus integral of px dx times, we have this integration. So for specific problems, of course, we will calculate this q, p, and we can make these integrations to come up with a closed form solution for the first order differential equation. Okay, here's an example. Dy dx minus y equals to e to the power minus x over 2. We have y of 0. This is our initial condition. So we want to solve this initial value problem. So we have y prime minus y equals to e to the power minus x over 2. And basically, we can now, let's go back just a second to see that this is y prime plus py equals to q. So what we have here, y prime minus y equals to, the right-hand side is given as q of x in our notation. So this is our q of x. Our p of x is just minus 1. That's the coefficient in front of this term. Therefore, we can easily calculate for this problem. We can apply the integration factor method, because this is easily can be integrated, e to the power px dx. So we obtain the integration factor. So once we obtain the integration factor, we will multiply both sides of the equation with this expression. So multiplying both sides here, we obtain this expression. Now on the right hand side, we have e to the power minus x, e to the power minus x over 2 from the original q of x here. And then basically now this is application of the product rule. That's the product e to the power minus x y derivative. So from this point, we need to integrate both sides, as we just mentioned, and then solve this expression with respect to y. And that gives us, first of all, this equation after we integrate, and we have an arbitrary integration constant, and then we divide both sides by this expression. And of course, we can integrate here. We can take the integration, calculate the result of this integration. And by doing this, as you see, minus 2 over 3, this is the result of this integral, plus constant, and divided by e to the power minus x. And finally, we obtain this result as the general solution of this problem. One more last step. We need to obtain the special solution because the initial value problem is given. So if x equals to 0, this will be 1, and this will be e to the power 0, which is 1, times c. So as we plug in these numbers, we can solve the value of c. And finally, this gives us the so-called special solution as this equation. Another example, suppose you have x squared plus 1, and this is the first derivative of y with respect to x. 3 times xy equals to 6x. Now, remember, we need the coefficient in front of this y. We need this term, dy dx. But we need this term alone, so we should divide everything by x squared plus 1. So we divide it by x squared plus 1, x squared plus 1. So this is my q of x, and this is my p of x from this form for the integration factor method. And by writing everything in this form, we can easily obtain that this is our p of x, and this is our q of x. Okay? So mu of x equals to e to the power integral of px dx. This is the integration factor. And mu of x equals to integral of 3x divided by x squared plus 1 dx. And we know that this is the integral of this expression times 3 over 2. And you can take this as a power of the x squared plus 1. And this gives us x squared plus 1 to the power 3 of 2, 3 over 2. And now, once we obtain the integration factor, what do? We multiply both sides of the equation with this term. This is the integration factor. So we multiply both sides of the equation. Here, you have both in both sides. And then we can observe that this left-hand side becomes the application of this product rule here. Okay, we have this expression and the derivative. And on the right-hand side, you have this expression here. Now, the next step is, as usual, take the derivative of both sides and add integration constant. Since this is the derivative and integral, so we reduce this as x squared plus 1 times y, integral of this expression dx. And basically, we can integrate this expression again. We know how to integrate this because the derivative inside is 2 times x, and you can write this as 6. Instead of 6, you can write this as 2x times 3. And we have this 3 over 2. When we take the derivative of this expression, you can verify that you get this expression here. Because 3 over 2 times 2, you have 3. And then the derivative inside is 2x. So that will give us 6x times x squared plus 1 to the power 1 over 2. So essentially, after you do this integration using your calculus knowledge, you get this term plus an arbitrary integration constant, and then divide all the terms by this expression, and that gives you y of x in this expression. So notice that this c is arbitrary constant, and here you can divide these terms. This is 2 plus c times x squared plus 1 to the power minus 3 over 2. And this is the general solution we obtain. So here's the example. We have x squared dy over dx, x times y equals to sine x, y of 1 equals to y of 0. So if you want to solve this, one more time, try to apply the integration factor method. You need to keep this guy alone. So divide everything by x squared, and you get this expression here. So this is your p of x, and this is your q of x. And once we identified these in the correct way, we calculate the integration factor, integral of px dx, and basically that's given as the e to the power ln x, the result of this integration. And that's equal to basically x. So our integration factor turns out to be just x. Multiply both sides of the equation by this integration factor. So you have basically x times dy dx plus y equals to sine x over x. Now the next thing is, notice that this left side is the derivative of this product. So we integrate both sides, and that gives us x times y equals to this integral plus the arbitrary integration constant. So in some numerical software, this type of integral is easily calculated. So for that purpose, you can represent this in a special form in order to apply the numerical functions in these numerical software packages, basically. Okay, so these are our examples. We have seen the integration factor method. We will stop here and continue in our next video.